Hello everyone, welcome back to the channel. In today's tutorial, we'll perform an eigenvalue buckling analysis of 3D connecting rod using ANSYS Mechanical 2025 R2. We'll begin with the CAD model, perform a static structural analysis under compressive loading, and then use that solution to predict the critical buckling load and buckling mode shapes. Before starting the simulation, let's briefly understand why buckling analysis is important. A connecting rod transfers force from the piston to the crankshaft and experiences alternating tensile and compressive loads during engine operation. Under high compressive loads, failure may occur due to buckling before the material reaches its yield strength. That's why engineers perform buckling analysis to evaluate the structural stability of the component. Here, I'm importing the three-dimensional CAD model of the connecting rod into ANSYS Mechanical. After importing the geometry, it's always good practice to inspect a model for missing faces, gaps, or geometry errors before starting the analysis. Next, I'll assign the material properties to the connecting rod. The Young's modulus, Poisson's ratio, and density define the stiffness and mechanical behavior of the component during loading. Using accurate material properties is essential for obtaining reliable simulation results. Now I'm generating the finite element mesh. A suitable mesh captures the geometry accurately while maintaining a reasonable computational cost. Next, I'll define the boundary conditions. One end of the connecting rod is constrained, while a compressive load is applied at the opposite end. These loading conditions represent the compressive force experienced by the connecting rod before performing the buckling analysis. We first solve a static structural analysis. This establishes a stress state caused by the applied compressive load. Now I'm inserting an eigenvalue buckling analysis. The pre-stress from the static structural solution is transferred automatically. Next, I specify the number of buckling modes to calculate before solving the analysis. The solution is now complete. Here we can observe the first buckling mode shape of the connecting rod. The color contour represents the normalized deformation pattern, showing how the component would deform at the onset of buckling. Also notice the load multiplier. This value indicates how many times the applied load must be increased before the structure becomes unstable. For example, if the load multiplier is approximately 37, the critical buckling load is about 37 times greater than the applied compressive load. Connecting rod is one of the primary components of an internal combustion engine. Its main function is to transmit the force generated by the combustion process from the piston to the crankshaft. During every engine cycle, the connecting rod experiences continuously changing loads. These loads alternate between tensile and compressive forces as the piston moves between the top dead center and the bottom dead center. Although the connecting rod is designed to withstand these cyclic loads, one important failure mode that engineers must consider is buckling. Unlike yielding, where the material fails because the stress exceeds its strength, buckling is a stability failure. Even if the stress remains within the allowable limit, a slender component subjected to compressive loading may suddenly deform sideways once a certain critical load is reached. This is exactly what we are going to investigate in this tutorial. Our objective is not simply to observe the deformation or to perform this analysis correctly. We first need to establish the stress state inside the connecting rod using a static structural analysis. The buckling solver then uses this stress state to calculate the critical buckling load and the corresponding buckling mode shapes. Now, let's begin the simulation. As you can see on the screen, I have opened ANSYS Workbench. Workbench provides a graphical environment where different analysis systems can be connected together. This allows multiple simulations to share information with one another. Connecting rod. Instead, we want to determine the critical load at which the material assignment is a fundamental step because every structural analysis depends on the mechanical behavior of the selected material. Properties such as Young's modulus determine the stiffness of the connecting rod. Poisson's ratio defines how the material contracts laterally when stretched or expands laterally when compressed. Density becomes important whenever inertia or self-weight needs to be considered. Notice how the software takes a few moments to complete the mesh generation. The time required depends on complexity of the geometry, the selected mesh size, and the computational capability of the system. Once the mesh has been generated, we can clearly observe that the connecting rod is no longer represented as a single solid body. Instead, It is composed of many interconnected finite elements. Each of these elements contains nodes at its corners or edges. During the solution process, ANSYS calculates the displacement at every node. From these nodal displacements, the software computes strains and stresses throughout the model. This numerical approach allows engineers to accurately predict the structural behavior of complex components that cannot be solved using simple analytical equations. Now I'm inspecting the generated mesh. This is an important habit during every simulation. Rather than immediately proceeding to the solution, it's good practice to rotate the model, zoom into different regions, and verify that the mesh has been created correctly. The deformation pattern displayed on the screen represents the buckling mode shape of the connecting rod. It is important to note that this deformation is not the actual displacement the connecting rod will experience during normal operation. Instead, it shows the shape in which the component is most likely to become unstable if the applied compressive load reaches its critical value. Another important result is the load multiplier, also known as the buckling load factor. This value indicates how many times the currently applied load can be increased before the connecting rod reaches its critical buckling condition. Thank you for watching this tutorial. I hope this practical demonstration has helped you understand not only how to perform a buckling analysis in ANSYS, but also how engineers interpret these results to make informed design decisions in real-world applications.